Right. Then the experiment 18. This is the last experiment today, right? This is critical angle method. This is very important practical as well, right? Determination of refractive index. Write down the topic. Write down the topic. Determination of practical 18. Determination of the refractive index of a material. Determination of refractive index of a material by critical angle method. By critical angle method. By critical angle method. Right? So for this experiment as well, we need a prism and optical pins. Right? So that is the way to do this as well. So this is the theory, right? You know that sin C, see the critical angle of sine value of critical angle is equal to what? N rare divided by N dense. Refractive index of rare medium, refractive index of dense medium, right? But in this experiment, what do we do? At the outside of the prism, it is air, right? And for the dense medium, we get a glass prism. So for sin C, for air in refractive index is 1. Air in a vacuum, refractive index is just 1. For dense medium, it is glass, Ng, right? So the goal of this experiment is to get a value for this critical angle. You need to find the critical angle. So once you find the critical angle, you know the sine value of that, then you can find Ng. Ng means prism material, right? Take this down. So for this as well, we have similar procedure, right? You can take this down as well. So you have the paper and a prism on the table. You can take this down. Then you are looking from above. Place in optical pins. Right. Earlier I missed a point. Remember that when we are finding a prism angle, we go for this complicated method, right? When you are finding prism angle, we went for this complicated method. But easily we can measure the prism angle, right? Just place the prism on a white paper. Then you draw the margins. Using the protractor, you can easily find a prism angle. This is for the previous practical, right? Previous one, not for this one. I missed this part. You can easily measure this prism angle. But why do we go for this complicated method? What's the reason? You can easily draw this one and measure this angle using the protractor. In both cases, we use the protractor, right? To measure the angle. What's the reason? The reason is, here you are measuring capital A. But here you are measuring 2A. 2 times A. So you know that when the measurement is higher, percentage error decreases, right? Or the fractional error decreases. Remember? So that's the only reason there, right? That's the only reason we go for this complicated one when we are finding a prism angle. Because fractional error decreases. Fractional error means least count divided by measurement, right? If the measurement increases, fractional error decreases. So that's the only reason there, right? Okay, just know that fact as well. Fractional error decreases there. That's why we go for a complicated method to find twice the prism angle. Right, that's it, right? That's now. Now this is the equation we go for this experiment. Sin c is equal to 1 over n. So if we find the critical angle, then you can find refractive index of the prism material, right? Then this image is very important. Don't draw, just understand what I'm saying, right? So you have this prism. In the critical method, right, you place a optical pin in contact with a side of the prism. So why do we use an optical pin? Why do we use an optical pin? Optical pins, the height of optical pins are usually uh, larger than the thickness of the glass, thickness of the prism, right? Otherwise, if this is short, optical pin is like this, right? You won't be able to place at the edge of the prism. It will be like this. So if the optical pin is, its height is enough, you can place the optical pin. So this is the thickness of the prism. You can place the optical pin like this. So that's why you need an optical pin for this one, right? Okay. So in this practical, in order to prevent the refraction of light rays coming from this pin, you need to place the optical pin in contact with this side. So it won't get refracted, right? It won't get refracted when you place in contact. So that's the first point. So if it doesn't get refracted, the rays from P goes everywhere, right? But we only need rays incident on the prism. You can think about a ray like this. You can think about this ray. A ray which goes perpendicular to this side. That ray doesn't get refracted from this side as well, right? Because it is perpendicular. Then we can consider a ray like this. Ray goes to this side. Draw a normal to here. Then what direction would this move? Away from the normal. It would incident here and move away from the normal. And it goes like this. Then you can think about a ray like this. Draw a normal. Then that also goes away from the normal. You always have to draw a normal, right? Otherwise you don't know whether it is away or not. So if you keep drawing, you can draw lines like this, right? To all the directions, rays goes. There's a particular ray, when it hits here, then the ray goes along the surface. So when this happens, we call this incident angle as critical angle. So this is the critical angle, right? So for the experiment, we have to identify this ray, right? In order to find critical angle. So that's the point of this experiment. So this is the important part, right? Important ray. So if you slightly increase, if you think about another ray that has a slight increase of, so as the ray is incident from this side, this angle keeps getting bigger. So if you slightly increase the angle, what happens? It causes a total internal reflection. But we say, because slight increase, C and this angle to be the same, right? Because there's not that much of a difference. So then what happens? Draw the normal, and this ray is trying to move to this side. Then it moves away like this. Then you can observe this pin. You observe this pin. Right? There's another important part here, right? If you think about another ray, let's draw one more ray. You can think about this ray. So it has a bigger incident angle than the critical angle. Obviously, this is going to be totally internal reflected. It reflects like this, right? So when it reflects, this angle is smaller. So the refracted angle also is going to be smaller. So that would come like this. So all the other rays would hit here and comes from this side. So you will see that as well, right? Those rays as well. So you have to move your eye from this side to this side in order to identify this ray. So what happens is suddenly, so what do you see here? What you see is image of P. Image of P is what you see. You see suddenly image of P disappears. That point is where you place those optical pins. You place these optical pins. Looking at that instant when image of P disappears. You place these pins, right? So that is what you do in the experiment basically. Just draw this and use a different color to draw this, right? Right. Another thing I have to say is this acts as this side, right? Acts as a mirror as well, right? So you have an object here. In a mirror, what happens? At the same distance, it causes an image, right? So that image should be along this line. This image, right? Here as well, it should be the case. I mean, this ray has to come like this, right? From this image. So this causes an image here. Then if you think about this side, all the rays follow this image. All the rays should come from this image, right? So it will be like this. Right. Draw these two lines as well. Write down pin, optical pin should be in contact with XY. Put XYZ, okay? XYZ. Optical pin should be in contact with XY. Optical pin should be in contact with XY. So refraction from XY side, refraction from XY side is prevented. Refraction from XY side is prevented. Then another to the same line, right? We need optical pin, an optical pin, since it is taller than thickness of the prism, since it is taller than the thickness of the prism. Then another point, move the eye from I means human eye, right? Move the eye from Z looking at XZ side, until the image of the pin, capital P, disappears. And place P1 and P2 in line with that. Right? So I just explained that, but when you are doing the experiment, you don't see none of those rays, right? You have to figure those out using what you know. This is all you know, that these are the rays that you would get there. You have the margin of the prism, right? So on the white paper, you remove optical pins and the prism. Then on the white paper, this is what you get. You get X, Y, Z. You can draw the margin, right? Then you get the drawing of this. Then you have a punch here, hole. This is the position of pin P. You have removed that, but you have the position of P. What else do you have? Another thing you have is positions of other two pins. This is all you have, right? Then other stuff you have to create in order to find these paths of light rays, right? The remaining parts are all just creations, right? Those are creations. Okay, these are creations, right? So what do we do first? We can draw image of this one. So if you think about this as a mirror, this side you can consider to be a mirror. And at the same distance, there is image of P. There's an image of P here. Then other creation is you can extend this line till it meets XZ side. Let's name it as capital L. Then what do? Then you have to draw this line. IL line. And at the intersecting point, we have capital M. Right? So this is a one line. But this should be inclined, right? This is inclined. This is a one line here. Coming from I to L. Optical pin P, optical pin 4, P4, P3, P4. Or P1, P2. Doesn't matter. So here you have capital M. This intersecting point, you can name it as capital M. Then what happens? Then you draw this PM line. So what do you have? PML. PML is equal to what? 2C, right? The critical angle, 2 times the critical angle. So once we know PML angle, you can just divide that by 2 and find the critical angle, right? So if you know the critical angle, you can calculate simple n. So simple n is equal to 1 over sine c, right? Then you can find refractive index like that. Got that? All we had is margins of the margin of the prism and the positions of these 3 optical pins. So using all those, you just do these creations. You do these drawings, right? They ask you to do these drawings, right? In the exam, they have asked. You can check those past paper questions. I'll send you the past paper questions to try those at home. They ask you to draw these lines, right? Okay. Take everything down. So from the blue line, all the blue lines are creations, right? Those are what we just drew. Those were not gained from the experiment, right? All we gained from the experiment is black color parts. These are just drawings, right? So to practice this, you have to do those past paper questions. I'll send those past paper questions on to the group. Clearly understand, you cannot draw PM line first, right? There's an order to draw these lines, understand? First, if you want, you can either draw PI or P1, P2 first and find capital L, right? You draw this line first and find this point I. Then you extend this line till you get to the intersection of XZ. Name it as capital L. Then you can draw IL line. So the intersecting point of IL line is PM. Then finally you can draw the PM. Understand? Then PML is going to be twice the critical angle. Then you can use half of that value to find the refractive index. Okay. Everyone done? Thumbs up, right? If you are done. Lasal, have you done that? Okay. Then we'll move on to the last part of this experiment. Write the topic, finding critical angle. The topic, finding critical angle finding critical angle for glass liquid glass liquid interface. Finding critical angle for glass liquid interface. Right? Okay. Now you have the prism, right? Here we need for the previous one it was glass air. For this one we need a glass liquid layer. So how to create a liquid layer? You get a microscope slide, put some water here, and place the microscopic slide here like this. Then due to the surface tension of water, you will learn surface tension later, right? Due to surface tension of water, this water sticks between the glass and the prism. It doesn't pour away, right? It just sticks to that, right? So here you have a thin liquid layer. Thin liquid layer. You can draw this with me. Thin liquid layer. Then this is microscope slide. Microscope slide. Right? And X, Y, Z. X, Y, Z. Okay. Okay, drew that. There's a liquid layer here in between microscope slide and the prism. Right? Microscope slide and the prism. So here as well, we are going to follow the same method, the earlier method, right? So you place the pin, optical pin here, in contact with XY side, optical pin. Then that is going to create image. Let's say this is PN. N is this one, right? Interface of the glass interface. Understand? It is the edge of the glass, this N. Not the end of the liquid layer, right? End of the glass layer. There's PN. So this glass layer, end of the glass edge, acts as a mirror and creates an image of P at the same distance I. Right? Now just forget that there's a liquid layer. Just forget for a while that there's a liquid layer, right? Only the prism is here, right? Only the prism is here. So what happens? This acts as a mirror and it creates an image here, at the same distance. So that's what mirrors do. There's no, forget this one, right? Only the prism here now. Right. Now we found I. Then for the critical angle causes here. It's still, there's no microscope slide, right? Only the prism, right? For the prism, let's say for this incident, then there's going to be a critical angle for this incident. Let's say for this one. Then what do we do? Then the image is coming from here, right? Then this has to go along here and gets incident to this side and get away. So this is the ray diagram which I drew earlier, right? This is the earlier ray diagram. Then we know that this is the C, right? This angle is C, critical angle. We found that earlier, only for the prism. But now there's a liquid layer outside. Liquid layer outside. So let's say what happens, whether the critical angle increases or decreases if there's a liquid layer. Remember this equation, right? Sin C is equal to what? N rare divided by N dense. Right? For the dense medium does not change. Dense medium is the glass, right? It does not change in both cases. But in this case, initially, for the previous case, this was 1, right? It was air. Now there's a liquid. Liquid has a higher refractive index than 1. So this is higher. So if this is higher, now the critical angle should be a large value compared to the previous one. Understand? Right? When there's a liquid layer here, critical angle increases. So how do we draw that? So if it is a large value, critical angle will be gained somewhere here, right? Somewhere here. Just draw this line. Let's say that happens here. Now you can clearly see critical angle is gained at a point somewhere here. Beyond this point, when there's a liquid layer, let's say that angle is C dash. Then the normal and the ray comes out. You place P1 and P2 pins here, right? For these ones, you do the same experiment. You move the eye from here to here. Then you place, when the image disappears, image of P disappears, you place P1 and P2 optical pins along that line, right? You do the same stuff. But here what you have to understand is that when there's a liquid layer, critical angle got larger, right? Compared to the previous critical angle, right? Take everything down. Write this one as well. Right. Then write a point. Write down, since at both cases, total internal reflection occurs at xz, position of capital I does not change. Position of capital I does not change. Understood? For the previous, when there is no liquid layer and when there is a liquid layer, we have the position of capital I to be the same place, right? Get it? But the image position changes, final image position changes. But this position of I does not change, right? In the exam, they ask questions from that. Then for this one, so sin c is equal to 1 over ng. We found this from the earlier one, right? Then sin c dash is equal to what? Instead of air, now we have the liquid. Let's say NL. So Ng is this one, right? So if you divide this by this, sin c dash divided by sin c, what do you get? Sin c dash is NL divided by Ng divided by 1 over Ng. Ng cancels off, you can find NL. NL is equal to sin c dash divided by sin c. So this is the refractive index of liquid. Take it down.